I guess we're up and running again. Okay. I decided to make my own video here about related rates. I'm going to talk about how the area of a circle changes with respect to time. And I'm a big believer in crunching numbers so that you can actually see something work, see some of these formulas actually play out. So that's what we're going to do here. I encourage you to replay different parts, stop the video. And this is your first foray into this material. I would have liked to have done more of these problems earlier, but at some point you have to put the brakes on and try to digest all the things that we've covered. Chain rule, product rule, quotient rule, implicit differentiation, differential equations, volumes of revolution, area between curves, respect to X and Y. I mean, it's a long list. All right, you got to practice that stuff in order to have a working knowledge. If all you do is, 3 days on a given topic and learn it for a test, well, I'm sorry, you're probably not carrying it in your long-term memory for very long. So again, we haven't done this topic as much as I'd like, but if you see the numbers work, then maybe some of those symbols in the differentiation process will have more meaning. All right, so stick with me best you can. I've got Shadow Lake. I'm sure you all recognized it. I didn't have to tell you that. It's the welcome hut on the road. Got the woods. It's warmed up, so I'm sure the ice is gone today. So nice out today. So that red circle in the center of Shadow Lake represents the area. Concentric circle is moving outward from a rock thrown into the water. Right? And obviously that is expanding at a certain rate. And I want to figure out at what rate the area is changing at a given instant. Okay, now the area for a circle is pi r squared. You can see that first column of data. And if the radius is 0, there's no area. Radius is 1. We get pi times 1 squared to pi times 2 squared, so on and so forth. And that represents square feet of area. Okay. And let's see, I can talk about some of this here. Let's see, I'm right to there. Okay, so that you can see that. I'll just bring this over and center it just a little bit more. All right, and I'll just talk right about here, and then we'll keep moving down the board. Everything's on the board already. So, I've got these rings out, which represent different areas at different moments. All right, and well, what if I changed the rate at which the radius is changing? What if that was a, almost, I hate to think of an explosion, sound wave, right? But that's going to move very differently than the rock in the pond. So the changing area is related to time. We'll bring those values in a moment. But I hope you can see that this black ring makes that red area a little bigger. So that's the layering process. And if I open it up, if I take one of those rings and open it up, well, that, I don't need the arrow here. I'm putting the arrow because each ring is successively bigger, which means that the change in area is getting bigger with respect to time. And the reason is the dr is independent, right? The same width of that rectangle, it's the same here as here, the same here, right? So if we unwrap it, that's why trig sometimes sine and cosine are called wrapping functions. If we unwrap this, that actually gives us the x-axis in trigonometry, radius length. Okay, but this, from the standpoint of geometry, well, that's the circumference. That's the circumference of the circle. The larger the circumference, the more rapidly the area is changing. Pi r squared, by the way, is a parabola, right? It's a parabolic relationship. And as we move along and we think about slopes of tangents, well, yeah, it's increasing. Bigger the area, bigger it's changing. Okay, so geometrically, what do we have up here? Well, we know the length at some instant is measured by the circumference. And if I want to measure that square foot area here, I have to look at how the radius is changing. A little bit of change, a little bit of change. And that's a rectangle. If I could blow it up a little bit, right? It's a rectangle. And so the change in area comes from length times width. Length times width, 2 pi r dr. Okay. And it's one little skip joint algebraic. This multiplier can come to the other side, and now we're doing a comparison. We're comparing how the area of the circle changes with respect to how the radius is changing. And we could create a table, and we could figure that out. We could approximate how this thing is changing in 3 by calculating 3.001, squaring it, and I guess that gets us 9.006 times pi, right? And we could do the change in area here to here over the change in the radius. And that's what we would be computing here, right? But what if I noticed as I sit by Walden Pond, no, Shadow Lake, I thought it was Walden Pond. Shadow Lake, did you see the fish? You saw the fish. Okay, I'm gonna try to catch that. No, I don't like to fish. I like to walk the water. I'll go with somebody else, but I don't want to put the worm on the hook. Ugh. All right. So what if over time I notice a relationship here to the size of the radius, the length of the radius? There appears to be a pattern here. Well, how am I going to get a feel for how this area is changing as time changes? Right? Instead of looking at column 3 to column 2, how it's changing there, what if I compare the change here to the change here? Well, I'm not over dr anymore. I'm over dt. Yeah. So how do I get a feel for that? How do I get a feel for that? And then I'll look at the symbolic process, and I'll check that out too. And if they match up, all right, that's how I get a feel for something. I'll go, I can trust that. So let's look. Again, I guess if I'm going to get a change in area with respect to time, then I got to change something. So I went with the littlest numbers I could think of. I made time 1 second. And we saw the 2-to-1 ratio over here. Still can see it, right? 1, 2, 2, 4. So hopefully you spotted that. Remember, pause the video at any time and think. So I'm going to go to 1.001. I'm going to use that as kind of a change, an instant. Boom. And I doubled it, 2.002. And I went to the calculator, and I suppose I squared it. I didn't need to really, but I squared it, 4.008 pi. And so I can see my change in area here pretty easily. Now let's keep moving down. Let's keep moving down. There we go. I'll make sure everything's pinned so I don't do this again. Repetition's my friend. So second area minus first area traps that area. That's the change in area from 1 second to 1.001 seconds. And the change in time from 1.001 minus 1 is 0.001 seconds. That's pretty instantaneous. That's approximating a moment in time. And so I looked at the change in area, 0.008 pi, divided by 0.001 feet squared per second, came out to 8 pi. Move the decimal 3 places. And I did that out just as a decimal, and I got 25.13 square feet per second. Okay, so what's that mean? That means my golf step used to be about 3 feet on a step. 3 feet on a step. And so if I walked 8 steps that way and 8 steps that way, then that's how much area is changing, but it's trapped. It's trapped in that ring, right? In that ring, 25.3 feet squared per second. Okay. It seems like a lot to me, but that's what it was. I'm gonna have to get out there and get in the water. Shadow Lake's kind of dirty now. We got to get to school to clean it up. Oh, where were we? Oh yeah. So we're gonna come over here and we're gonna go back to where we were before. The change in area, 2 pi r dr. But we're trying to find the change in area with respect to time. Geez, if I'm going to do that algebraically, I got to do it over here too. And we saw what the change in R with respect to t is in this table. By golly, that's 2 to 1. And the radius at 1 second, that's we're trying to find this at t equals 1, time equals 1 second. Okay. Well, 1 second, the radius is 2. Oh, and dr dt is 2. That's 2 feet, right, per second. Yeah. And this is when r is 2 feet. Well, that sure gives me square feet per second, doesn't it? Gives me square feet. And if we plug in the 2 and the 2, by golly, I get 8 pi feet squared per second. And if when I looked at the decimal over here for 8 pi, I got 25.13. I got a feeling that the calculator is going to give me the same answer over here. 25.13 feet squared per second. And of course, I didn't show everything there. Almost got through an entire video without having to think I got to do it again. Well, I'm not going to do it again. All right, so 2 pi r dr, I think we saw that. So what we didn't see was plugging in the numbers, because at 1 second, the radius is 2. So I got to plug in a 2. And I can see that there's a 2 to 1 dr dt. Change in r, change in time. So there's another 2 feet per second. And so I've got 2 times 2 feet times 2 feet per second. And that's 8 pi square feet per second, which is the same thing we had over here. So it sure looks like if area equals pi r squared, I don't know why I did capital R, but I did, then that seems to be true. So I guess the hard part is thinking about that. But that was the whole purpose of the video. Bringing in another component of change, right? So give it some thought. Getting to the end of the term, I wish we'd had more time to do more of those, but it was probably one of the last things that I highlighted. So I made a video, and good luck, because I'm going to be asking some of these questions on tests. And we got 2 more. So good luck.